Welcome to IT.Solution, your total network, system, firewall, and security partner.
Have you ever actually stopped to think about how a digital photo, a simple collection of software pixels on your screen, turns into a physical pulse of light racing across an ocean? It's literally a journey that takes data from the abstract realm of software right down into the tangible, physical hardware that wires our planets. Welcome to This Explainer. I am so thrilled to have you here today. We're going to strip away the user interfaces and the apps and look directly at the foundational hardware that makes the internet actually work. Today, we're diving into ITN Module 4, entirely focused on the physical layer. All right, here is our roadmap for today. We'll be hitting the physical connection, components, encoding and signaling, understanding bandwidths, copper cables, fiber optic cables, and finally, wireless media. Section 1, the physical connection. So, before any high-level network communication can even happen, we've got to build a foundational link. You'll notice the physical layer is a completely different beast from the rest of the network stack. Upper layers, like TCP/IP, they're all software, but this physical layer right at the bottom is pure hardware. We're talking electronic circuitry, cables, and connectors. And because it's hardware, it's governed by heavy-hitting telecom organizations like ISO, EIA/TI, ITU-T, ANSI, and the IEEE. Okay, so what is its actual job? Basically, the physical layer transports bits across the network media. It grabs a fully formed frame from the data link layer right above it, and its sole purpose is to encode that frame into a series of signals. This is it, the exact moment our digital data literally hits the physical road. Section 2, components, encoding, and signaling. Let's zoom in a bit. What actually makes up this physical layer functionally? Well, the standards here address three very specific areas. First, the physical components, your NICs, cables, and connectors. Second, encoding. And third, signaling. Let's look at how those last two work together. You see, together, encoding and signaling take those abstract ones and zeros and turn them into something real. Encoding formats the bit stream so the next device in the path can actually recognize it. Then signaling decides exactly how those bits are represented as physical energy on the medium. Depending on what you're using, that energy could be an electrical voltage, a radio wave, or even a literal pulse of light. Moving right along to Section 3, understanding bandwidth. Now, once we're blasting these signals out there, we need to know how much data we can actually push through these digital highways. The absolute baseline unit for this, 1 bit per second, or 1 BPS. Digital bandwidth is just measuring capacity. How much data can flow from point A to point B in a specific amount of time. And obviously, that capacity scales up big time, depending on your media and the tech you're using. We don't just hang out at bits per second. We jump up to thousands with kilobits, millions with megabits, and billions with gigabits per second. To put that into perspective, modern Ethernet standards can scale from a modest 10 megabits all the way up to an insane 400 gigabits per second. Section 4, copper cables. Think of copper as the highly reliable, heavily utilized local roads of our network. Take unshielded twisted pair, or UTP cables, for example. This is your classic everyday copper cabling. Devices use these to transmit data over electrical circuits, sending impulses right through the metal wires tucked inside that plastic shielding. Now, copper is great for sure. It's the cheapest option and super easy to install. But, and it's a big but, it has a major Achilles heel. Because it relies on electrical impulses, it is incredibly vulnerable to electromagnetic interference, or EMI, and radio frequency interference, RFI. Seriously, if your copper cable runs too close to a powerful electrical source, your ones and zeros are going to get completely scrambled. Which brings us to Section 5, fiber optic cables. If copper is the local street, fiber optic is the state-of-the-art bullet train. Instead of electrical impulses that pick up interference, fiber transmits data using literal pulses of light shot through impossibly thin strands of glass or plastic. And because it uses light instead of electricity, it is completely immune to EMI and RFI. Plus, it can carry data a whole lot faster over vastly longer distances. But, of course, that kind of high-end performance comes with a catch. Fiber optics require way more skill to install and strict safety protocols. The engineering is just incredibly precise. You've got specific connectors like ST, SC, LC, and duplex multimode LC, all designed to make sure those delicate little light pulses align perfectly from one device to the next. Finally, Section 6, wireless media. All right, time to take our bits completely off-road. Wireless media gives us ultimate mobility by carrying signals using radio or microwave frequencies. And to keep this from turning into total chaos, the IEEE set up some very distinct standards. We've got Wi-Fi governed by 802.11 for our local networks, then Bluetooth at 802.15 for personal stuff, plus WiMAX and Zigbee. Each of these carefully dictates the frequency, the power, and exactly how the signal is encoded. That being said, wireless isn't magic, right? It's still a physical layer medium, which means it has physical limits. Signals drop off when they hit walls, they deal with interference, and they have built-in security risks. But maybe the biggest thing to remember is that wireless is a shared medium. Every device in range is literally fighting for the exact same invisible airwaves. Which really leaves us with a fascinating question to ponder. As our networks keep growing and our hunger for bandwidth just completely explodes, how are we going to engineer our way past the physical constraints of these shared wireless spaces? The digital world feels totally invisible, but as we've seen today, it's strictly bound by the very real, tangible hardware we just explored. Thanks for joining me on this explainer, and keep questioning how your data moves.
Thank you for watching. See you in the next episode.